been a rapidly developing field. It goes under the name of generalized global symmetries, where we study generalizations of global symmetries and how we can use them to understand, to probe quantum field theory in regimes where perturbation theory might not be so helpful, and also to characterize various phases in the infrared. So it's based on, my lecture is going to be based on this lecture notes that stemmed out of a series of lectures at Oxford University last year. And it aims to provide an introduction to this field of generalized global symmetries. So as I already said, generalized global symmetries are generalizations of the usual notions of global symmetries. And there have been various types of such symmetries that have been discussed. Probably the most popular of them are what are known as higher form symmetries, which will be the topic of today's lecture, and also the second talk by Ludo. Then there are extensions of this, which are known as higher group symmetries, which describe extensions of higher form symmetries. We won't be delving into this topic. Then another area, another type of generalization going under the name of non-invertible symmetries has been extremely popular in the recent years. And this will be covered by the third talk, in the third talk by Arthur. These non-invertible symmetries are closely related to what are known as categorical symmetries, which have been studied in two dimensions, two space-time dimensions for a long time. And only recently they have begun to be understood in higher space-time dimensions. Then in more non-relativistic systems, there are other kinds of generalized symmetries like subsystem symmetries, exotic symmetries, sometimes called fractonic symmetries, etc. So as this is a lecture, the citations will be quite rare. So I have one over here, which is one of the fundamental papers that initiated this field in its modern language. And it mainly discussed higher form symmetries. If you want an exhaustive list of citations, I refer you to the set of lecture notes. Okay. And I should mention that before I begin, please feel free to stop me at any time if you have any confusion or any question. So let me begin with a preview of what we will see today. So we will see that these higher form symmetries are actually ubiquitous in cases of interest in particle physics. So they are ubiquitous in abelian and non-abelian gauge theories, which are the building blocks of particle physics. And the way one can use these symmetries is by utilizing the fact that they are actually invariants of RG flows. So, and so if you know the symmetries of some ultraviolet theory, you can constrain the infrared physics of that theory, even if it's strongly coupled. And the infrared physics can be gapped or gapless, or in more standard terminology, massive or massless. So here by gapped, I mean that there is some vacuum in the infrared, and the smallest excitation above that vacuum requires some energy gap. And gapless means that you have some massless fields in the infrared or some generalization of that like conformal field theory. So the possibilities for gapped infrared physics can actually be tremendously constrained, even though there are constraints on infrared physics for both gapped and gapless. In the case of gapped, it turns out that one can actually perform a full classification of such kind of things if you know the symmetry. So that's quite a remarkable application of these symmetries. And then utilizing this, we will see applications in understanding confining and deconfining phases of asymptotically free non-abelian gauge theories, which, as you know, is a non-perturbative problem because the gauge coupling becomes strong in the infrared and it's hard to determine whether the theory is confining or not. Okay. So now let me get into the main topic. So as a motivation, consider a standard global symmetry that we are quite used to. Say we are considering a U1 global symmetry. So one can keep in mind the example of a free complex scalar, and the U1 symmetry is just the rotating the phase of this complex scalar field. You can describe the Noether current for this symmetry, which takes the following form. And this is conserved by simply the equations of motion. So this obeys its divergence is 0, which follows just from the equations of motion. So this is the standard setup that we are quite used to. And then one can study various notions associated to such a symmetry, like what are the charged operators. So the operators that are charged under it are well known. They are local operators. There are some polynomials of this field. And so you can have things like phi squared, phi bar, etc. These will have charges 1, 2, and 1 respectively. So now all of this can be phrased in this nice diagram over here, which will be quite useful for us. So here we have we are displaying a Ward identity. So this space-time, I will be drawing space-time diagrams, which will often denote Ward identities. So here is some operator O that carries some charge Q under the symmetry, and these charges are valued in integers. And moreover, you have some operators that you can define, which are extended operators. They're codimension 1, and you define them using this Noether current. So what you do is you integrate a Noether current on a 3-sphere surrounding this local operator. Here n mu is the vector which is normal to this 3-sphere, and you can contract it with j mu and integrate it over the whole sphere. When you define it, you can actually define a whole circle family of these operators parameterized by alpha, which is a U1 valued element. And then this set of operators, you obtain a circle family of codimension 1 operators. These can be thought of as the generators for this U1 symmetry. So the U1 over here is precisely this U here. And then the fact that the operator carries a charge Q is encoded in this Ward identity that you can replace in a correlation function, something like this, by e to the iq alpha times the operator alone. So you just the local operator, you don't have any more the codimension 1 operator. And the charge Q appears over here as a coefficient of alpha. So this is the transformation law of the operator O under the global symmetry, phrased as a Ward identity. So are there any questions so far before I proceed?
Sorry, could I just ask about why do you call it a codimension 1 operator, the exponential?
Could you repeat that?
Why do you call this exponential thing a codimension 1 operator? What is it? Is it because S3? Yes. Is that why? Yeah, it's called the codimension 1.
Yes. So but I will. So dimension of operator for me would be the dimension on which it lives. So what is the dimension of submanifold in space-time over on which I can insert this operator. So here we have this operator. Yeah.
So it's inserted in a 4-dimensional space. So that's why it's codimension 1.
Yeah, codimension 1 in space-time. Yes. And 4 is the space-time dimension I'm going to work with throughout the talk. Yeah. So later I will describe Lakshya. How this can. Yeah.
Sorry.
Hello.
I'll ask in a second.
Can you go ahead, please?
Sorry, I'm confused why you call this the Noether current. That's not what I know in complex scalar field.
Yeah, so coming back to the previous question, so I defined this operator over here, which is codimension 1. It's only on S3 at the moment. I will describe how you can actually define it on any codimension 1 manifold in space-time in some time. Okay.
Sorry, I had another quick question just to be sure. It's not alpha in U1, it's e to the I alpha in U1, right?
Yes, of course, yeah. Thank you. E to the I alpha is in U1. Yeah, alpha is in R mod Z.
Sorry, I also have a question. Any field charged under this U1, so its charge must itself be quantized, right? But, I mean,
yes.
This is in other words, in the second equation that you write, phi going to e to I alpha phi, there should be a q phi, which is an element of z.
Right. So here I was looking at just this scalar field phi. So of course for phi squared you have it.
But this phi is itself an operator charged, I mean, is the simplest example of an operator charged under this U1, and its charge is itself quantized. So alpha cannot be just anything, because alpha plus 2 pi is the same thing as alpha, no? So
yeah, so here we have a charge 1. So it follows from this identity. If you put q equals to 1 over here, under an arbitrary U1 transformation given by some element alpha, this is the transformation for the operator phi.
yes. Okay, I see. Yes. Yeah. Anyway, but you agree that it's quantized itself. Yeah. Okay.
Yes.
Right.
Yeah.
Thanks.
Okay. Any more questions? Okay. So, so I want to focus this talk again. So I'm going to frequently focus this talk by discussing a physical example or a physical application of these symmetries. And what I will have in mind would be what are its constraints on the infrared. So here for this kind of usual symmetry, there are two possibilities. Either it spontaneously breaks or does not. And when it spontaneously breaks, what it means is that you have some charged operator in your theory, which acquires a non-zero vacuum expectation value. And in this specific example, this can be achieved, for example, using Mexican hat potential. And then the consequence of U1 symmetry is that in the infrared, we obtain a massless Goldstone mode, which is a scalar field, which is a compact scalar, and it can be understood as fluctuations of this field phi in the infrared. So if you have the symmetry and you spontaneously break it, then it leads to a physical implication, which is the existence of Goldstone mode. And we will see something similar in the example of higher form symmetries. So let me motivate these higher form symmetries by considering the simplest type of such symmetries. And these are known as one form symmetries. So I will describe the terminology of P form symmetry, what it means. But first we begin with this example. So so there can be other conserved quantities which are not quite a space-time vector, like the Noether current. So take, for example, the pure Maxwell theory. This is, we have an abelian U1 gauge theory without any matter. Lagrangian schematically takes the following form. And then we can consider a Noether current, which is simply F mu nu, the field strength. This is two indices in space-time. It's not a current it's not a vector anymore. And it also obeys a conservation equation, which takes the following form. And the fact that this is conserved follows from the equations of motion for the pure Maxwell theory when there is no matter present. And this equation is a typical equation. We have seen it many times. It simply captures the conservation of electric flux. So one can think about whether we can regard this as a symmetry. And now you can, using the similar gymnastics as for the usual symmetries, one can find what the symmetry action for this is, for which this would turn out to be Noether current. And the symmetry action takes the following form. So you take your gauge field, and so the usual gauge transformations are that you add some exact one form to it, but you can consider adding a closed one form. So here we have a lambda mu, which is a one form, which is closed. Here I'm using the differential form notation. And this is the action of this symmetry. And again, you can see that this action is U1 because A mu is circle valued. So famously, there is a large gauge transformation on the gauge field, which makes gauge field a circle valued quantity. Okay. One can also discuss charged operators for such a symmetry. So these charged operators now are some electrically charged particles. We don't have such dynamical particles in the theory, so they have to be probed. We have to insert them as probes, or in other words, they need to be infinitely massive. And then this symmetry measures how much electric flux is induced by the presence of such a particle. So these particles are charged under this one-form global symmetry. And again, one can express this as a word identity shown over here. So these charged particles can be understood as line operators. So as operators that live along a line-like locus in space-time. And we are familiar with them. So they are also known as Wilson line operators. And they can be described in this form. So a probe particle of charge Q couples to pure Maxwell theory by an insertion of a factor like this in the path integral, where Q is a quantized charge. And then integral of A is the integral of A along the line that we have chosen where we are inserting this operator, or the world line of this probe particle. Along this line, we are integrating the gauge field A, which we can think of as a one-form field and can be integrated naturally along a line. So this is the Wilson line. And then one can measure its electric flux. So one can imagine that there is a space. So there is some space slice over here, and inside it, this appears as a point particle. And surrounding it, there is a two-sphere on which we can integrate this operator J mu nu using two normal vectors that are available now in space-time. And that would measure the electric flux around this probe particle. And the result can be expressed as a word identity. Where now one can remove this. This is now a co-dimension 2 operator. So it's two-dimensional in space-time over an S2. One can remove this at the expense of introducing a phase. So this is completely analogous to the usual symmetries, where we had point local operators that were charged, and the symmetry operators were co-dimension 1. Now symmetry operators are co-dimension 2, and the line operators are charged. So there is this, if one of them increases in dimension, the other one decreases in dimension. Are there any questions at this point? Okay, so this is the simplest example of a one-form symmetry, a U1 one-form symmetry. And one can ask, what are the possible physical implications of this? Why should I care about such a symmetry? Again, let's consider its spontaneous breaking in the infrared. So let's keep the example of the Maxwell theory in mind. then there is a standard Lorentz invariant vacuum that it has, in which this gauge field takes zero expectation value. I mean, it's because it's Lorentz invariant that fixes that the only possible wave for gauge field is trivial. And now you can see that a transformation of this form, shifting a mu, is indeed broken in this vacuum. It shifts one out of this vacuum. So this U1 one-form symmetry of the Maxwell theory is spontaneously broken without having to introduce any external potential or anything like that. In the standard Lorentz invariant vacuum, it's broken spontaneously. And then one may wonder that there should be a Goldstone mode associated to breaking of such a continuous symmetry. So Goldstone modes are fluctuations of the gauge field, A mu, and we recognize them. These are simply the photons. So the conclusion is that photon should be viewed as a Goldstone mode for a continuous U1 one-form symmetry. So spontaneous breaking of such a symmetry. One can look for another perspective on the spontaneous breaking. Just like for the usual symmetries, spontaneous breaking corresponds to charged operators acquiring a non-zero wave. We can ask whether these charged operators, these probe particles that we discussed, do they also acquire a non-zero wave in this vacuum? So what would this even mean? How can a line operator acquire a number which is non-zero? Because a line operator is something which stretches across space-time. So one of the simplest things to do is to compactify the line operator in space-time. And the way to do that is you can put it on a circle or on a rectangle as shown over here. Let's say the sides of the rectangle spatially, it is R, and there is one direction along time, which is T. And now we wrap one of these Wilson line operators of charge Q along such a rectangle. So for large values of the spatial distance R, this looks like two probe particles that we are trying to separate from each other. So they were created at some moment of time, and they will be annihilated in the future at some moment of time. And in between, we are measuring the transition amplitude for them to stay at a certain distance. So now there is a standard computation that one can perform for large R and T. In the Maxwell theory, this can be shown that this correlation function goes as exponential. So I'm doing a Euclidean calculation now, which is why there is this minus sign in Euclidean spacetime. So it goes as exponential of minus the potential between these charged particles, which is a function of R times the time interval T. And this potential is the usual Coulomb potential. So this is V of R is just 1 over R. And now we know what happens for a Coulomb potential, for example, from gravitational physics. It is possible to infinitely separate two charged objects in a theory with Coulomb potential infinitely far away by expending a finite amount of energy. So you can physically separate them infinitely far away, which means that you can arrange for it to have a non-zero correlation function for very large distances of R and T. Or in other words, these operators survive in the infrared theory. You can separate them to very large distance scales, and they survive in the infrared and become some operator of the infrared theory. In other words, you can say that it acquired a non-zero wave. It has an expectation value in this vacuum.
Sorry,
Right. So,
Lakshya, can I interrupt you? So these photons are soft photons, right? or any
Yeah.
photons?
What do you mean by soft photons?
Yeah, because you said that we can think about photons and go as Goldstone modes, and then I was naively thinking that you're talking about large gauge transformation. That's why I had this idea. So it can be any photons with any momentum, or just in the IR limit.
No, any photons. Yeah, I mean, so I'm only looking at fluctuations, small fluctuations of the gauge field, which when you quantize become the photons. Yeah, I'm not sure whether it's important for these photons to have a limited amount of energy, or whether they can have a large amount of energy.
I was just naively, I just try to understand if this lambda mu is a local gauge transformation or a large gauge transformation, maybe.
Right. Sorry, so this is not a gauge transformation. This is a one-form symmetry transformation. So this is what I was emphasizing. So yeah, so a large gauge transformation will be of the form.
I see.
A
Now I
mu
see.
goes
Sorry. Now I see. Thank you.
something like this. So it will be an exact one form, but this is just some arbitrary one form which is closed.
Yeah. Thank you. Thanks.
Yeah. Right. So we have shown that because of this Coulomb potential, the line of the probe particles can be separated infinitely far away, which means that they survive in the infrared. And one may say that they have a non-zero vacuum expectation value in this vacuum. So this indeed corresponds to, there is indeed a parallel between the usual story of spontaneous symmetry breaking, where you have some symmetry transformations that don't leave the vacuum invariant, and you have charged operators, which acquire non-trivial webs, which can be found in the infrared theory. In this one form symmetry example, there are exactly the same patterns. So you have symmetry transformations that do not leave the vacuum invariant, and you have charged operators which survive in the infrared. So they obtain some non-zero wave. So the main lesson from all of this is that one can think of Coulomb phase of a gauge theory as spontaneous breaking of a U1 one-form symmetry. So this is in this way you can characterize the Coulomb phase of a gauge theory in terms of Landau paradigm, which tries to characterize phases in terms of whether some symmetry of the system is spontaneously broken or not. And this is an extension of it, applying this Landau paradigm to these new kinds of one-form symmetries. In particular, U1 one-form symmetries leads us to a characterization, a Landau characterization for this well-known Coulomb phase of gauge theory. So yeah, let me pause here and ask whether there are questions about this.
Yes, I have one. I was thinking about these photons method, and what happens when there is matter in the theory? Because then the equation of motions change, so the df is not zero anymore. So you don't have this symmetry. So what happens to the Goldstone boson? I mean,
yes.
This is
So
two questions.
Right. So yeah, that's a very nice question. So about the Goldstone boson, so there are two types of situations to consider. So we have a matter field, and this F mu nu is not closed anymore. So we won't have a one-form symmetry anymore. But now there are two cases whether you have a massless matter or a massive matter. So in the case of massless matter, then another one is massive matter. Phi is some matter field which is charged under the gauge group. So in this case, you have an emergent infrared symmetry below the scale of the mass scale. You obtain an emergent U1 U1 one-form symmetry, which then spontaneously breaks. So this exhibits spontaneous symmetry breaking, leading to a Coulomb phase in the infrared again. In this case, there is photon, which cannot be interpreted as a Goldstone mode. So there is never an emergent one-form symmetry. So photon is not a Goldstone mode. But crucially, the phase is also not a Coulomb phase. So this the potential is modified because of the renormalization of the electric charge of these Wilson lines. So the potential in this case takes some form like I think something like 1 over r log r. So it's not quite the same phase anymore. It's sometimes called as a free electric phase to distinguish it from the Coulomb phase. So yeah, so just to conclude, the Coulomb phase can be interpreted as spontaneous breaking of a U1 one-form symmetry, which may be there completely in the ultraviolet or maybe emergent. But the photon may or may not be viewable as a Goldstone mode always. Does that answer your
Thank
question?
you. Yes, thank you.
Was there another question?
Yes, I have a question. So I'm still thinking about the difference between the local gauge transformation and the one-form gauge one-form transformation. And you know that the local gauge transformation is a redundancy. It's not true symmetry. So I wonder, is this transformation really happen in closed one-form modular exact one-form? I mean, in the quotient space. Is that true?
Yes.
Okay, I see.
That's correct. Yeah, the exact ones are gauge transformations, and the closed ones are one-form symmetry transformations. They are global transformations.
Okay, thanks.
Yeah.
Sorry, I had a related question. So in your slide before, you write mu is 0 equals 0 is the Lorentz invariant vacuum, but I don't understand that statement. Mu is not observable. So what do you mean exactly?
This is in a gauge fixing. I'm assuming I have used a gauge fixing. Just like in Higgs mechanism, you have a scalar field which is charged under gauge group, but you talk about giving a wave to it. Yeah. Does that answer your question?
Yeah, thanks.
Sorry, related to the previous question, I wonder, maybe you can have something like Berry phase, or if you couple that to fermions, you can have Boharonov-All phase. Can you somehow relate this formalism to them, or if it's unrelated, we can discuss later. Thanks.
Yeah, so these Aharonov-Bohm phases are related to generalized symmetries, not quite in this context, but in 2+1 dimensions, there are phases shown by Aharonov-Bohm phases shown by anyons, and they're related to braiding properties of line operators, and they can be thought of as 't Hooft anomalies for some one-form symmetries. This is going into slightly away from the main discussion we have over here, so maybe let's discuss later.
Yeah, sure. Thank you.
Right. So any more questions? Okay, so let me proceed. So here is a table for defining in some sense what continuous higher form symmetries are like. So the usual symmetries in this language, so this is just introducing some language. So in this language, the usual symmetries are known as zero form symmetries. Sorry. Yeah, zero form symmetries. And then the Noether current for them has a single index in space-time. The charged operators are local point operators, and the symmetry generators are codimension 1 in space-time. And this can now be extended to any space-time dimension, not necessarily 4. Then we saw an example of one-form symmetry. So in general, one-form symmetries, continuous one-form symmetries, have Noether currents which have 2 indices, which are anti-symmetrized. So in our previous example, it was F mu nu. The 2 indices were anti-symmetric. The charged operators are 1 dimension higher. They're line operators. And the symmetry generators are 1 dimension lower. So they're 1 higher codimension. And always the charge is computed as a word identity by linking these operators so the symmetry generators with the charged operators. Okay. Then you can similarly think about 2-form symmetries, which would have 3 indices, all anti-symmetrized. The charged operators would be surface operators. And the symmetry generators are a codimension 3. So in 4 space-time dimensions, some examples of theories which exhibit 2-form symmetries are gauge theories with a discrete gauge group. Which are or BF type theories in 4 dimensions. And then one can continue to talk about 3-form, 4-form, etc., which are more relevant to higher dimensional quantum field theories, higher than 4. So this is the dictionary of higher form symmetries. The generalization is follows in this pattern. And before moving ahead, I want to stress a point because this will lead to this is the key for all of the generalizations. And the point is that the symmetry generators that we have been talking about, which are these extended operators of codimension 1 or codimension 2, they are not some arbitrary extended operators. They are very special operators, which are known as topological operators. So what this means is that if we are computing a correlation function in the presence of such an operator, one can deform the location of these operators topologically without changing the correlation function. So the correlation functions only see the topology of how the submanifold that it is wrapped on is embedded in the spacetime. So let's see how do we show that these are topological operators. Okay, so let's begin with the usual case of usual symmetry. So we want to show that the symmetry generators are codimension 1 topological operators. So we begin with the Noether current that we have. This is a vector in space-time. Using the Levi-Civita tensor, one can convert it into a 3-form. Let me call that J3. Similarly, if you have a 1-form Noether current, you can use the Levi-Civita tensor to convert it into a 2-form, and so on. Now the conservation equation in terms of these forms can be expressed as the fact that these forms are closed as differential forms. So for the usual 0-form symmetry case, it's in 4 dimensions, it's a 3-form that's closed, and for 1-form symmetry, it's a 2-form that's closed. And one can now choose some. So let's say I'm dealing with one. Let me call this label as P. I'm dealing with a P-form Noether current. I can choose a arbitrary P-dimensional submanifold of space-time, MP, and define a U1 collection of operators, which will be denoted by U alpha, where alpha is the U1 element. And this you define it by integrating this P form operator on this P manifold and exponentiating it. So this is the definition. So this is in response to a question that was asked previously. We had defined the codimension 1 operators only on S3 and codimension 2 operators only on S2. Now we have defined them on arbitrary codimension and codimension 2 manifolds. So let's see how we show them that they're topological. So this can be quickly done by, let's consider a deformation of this kind of the manifold, where we're deforming a P manifold by the boundary of a +1 manifold. Then one can simply using this relative write this as the operator at the location of the original manifold MP times the integral on the boundary of this P+1 manifold. Using Stokes' theorem, this is the same as integrating the derivative of the P form current on the P+1 manifold. And since this exterior derivative vanishes from the equations, this term drops out. So you have shown that the deformation invariant, or in other words, a topological operator. So how one can think of now higher form symmetries isn't as follows. The usual symmetry are dimension topological operators. And then as one generalizes the codimensions of these topological operators, one obtains the other higher form symmetries. Are there any questions about this? Yes. So now let me come to a point which was already mentioned in one of the questions before. What happens when we add matter to the system? So again, let's return to our Maxwell theory example, and let's add a matter field. And let's say the matter field phi hat 1 could be a scalar, fermion, or any kind of field. I'm just calling it phi. Then this equation is no longer true. The field strength is not divergence-less anymore. And hence we cannot construct Noether current. So we don't have a one-form symmetry anymore. And this can be physically understood as follows in terms of these pictures. So we know that the probe particles for this kind of one-form symmetry are Wilson lines, are charge Q Wilson lines, which will possibly be the charged operators. So let's try to measure the electric flux again, where I'm using the differential notation of such a charge Q Wilson line. So in this configuration, it would simply pop out the usual to the IQ alpha. But since we have this matter field, we can excite particles for it as well dynamically. So in the path integral, there will also be configurations of the form where Wilson line is screened by some dynamical particles. So here phi is simply a shorthand for saying that we have a charge K dynamical particle that's also threading through this process. And now if you measure the charge, you obtain e to the I plus K alpha. So in the whole configuration inside the path integral, there is no fixed charge for this Wilson line. For all of these various contributions sum to 0. This is often intuitively expressed as follows, that if you have matter field, then it screens the charges of probe particles. A cloud of matter field screens the charges of these probe particles. So we have screening and we don't have one-form symmetry anymore. But we can consider another kind of situation. We can say that the matter field, instead of having charge 1, charge 2. So now let's repeat this intuitive exercise again. So the original configuration gave us e to the IQ alpha, and any screened configuration gives us e to the IQ plus 2k alpha. So if you substitute alpha equals to pi, you are able to observe a definite physical quantity, which is -1 for this and -1 for this, since 2 times pi is 0. So in other words, the one-form symmetry corresponding to alpha equals to pi survives. It can be measured now. And the one-form symmetry is in fact Z2 in such a theory, whose generator can be expressed now. The symmetry generator can be expressed like this, e to the I pi integral f. And the Z2 charge of a Wilson line is simply its electric charge modulo 2. So this example is to show that we can not only have higher form symmetries that are continuous, but we can also have discrete higher form symmetries, like this group Z2. And in general, if you have a charge P particle, you will have a ZP one form symmetry. For such discrete higher form symmetries, we do not have Noether currents. And the only definition that we have available is the presence of topological operators of an appropriate codimension. So that's the most general definition of these symmetries. Right. So here I'm saying, again, emphasizing this point, that one should really distinguish between discrete and continuous higher form symmetries. The continuous ones have conserved Noether currents associated to them, while the discrete ones do not have conserved Noether currents associated to them. But what is common between the two is that there are topological extended operators in the theory, which act as symmetry generators. So the definition of a final definition of a P-form symmetry, which works both for continuous and discrete cases, is as follows. A P-form symmetry, we say that we have a P-form symmetry group GP inside a theory. If there exists codimension P plus 1 topological operators, whose composition is described by the group laws. So there exist topological operators which are described by elements of this group. And if you try to compose them together, you bring them very close to each other and perform a fusion process. Then this composition is described by the group multiplication. Okay, so are there any questions at this point? Okay.
Well, I have a question. I don't know if it's directly related to this one. I was wondering if Bianchi identity can somehow lead to some quantity here.
Right. So yeah, that's a very nice question. So Bianchi identity corresponds in terms of field strength to star F, in terms of differential forms to star F, and this is always sorry. Right. So it corresponds to star F, which is always closed. So we always have, and this is even in the presence of matter. So we have a U1 one form symmetry in 4 dimensions. In any abelian gauge theory, even if irrespective of whether it has matter or not. So this one form symmetry is different from the one form symmetry that we have been discussing, which is associated to the field strength. And they are often distinguished by saying that this is a magnetic one form symmetry, and the one that we have been discussing, the one corresponding to df equals to 0. Sorry, I messed it up. Sorry, this one is the one that we have been discussing. It's the electric one form symmetry. It can be broken, and the Bianchi identity df equals to 0 is the one which is magnetic and is always there. Yeah, so this is the Bianchi.
Thanks.
Yeah. Okay. Any other questions?
Yeah, sorry. Can you say can you explain a bit more what it means to compose the operators, to bring them together? I mean, they're defined by some extended things. What does it mean?
Right. Yeah, so let me use this space over here. Yeah, so these are some extended operators. So let's say this is one such operator, which is wrapped on some manifold. I'm looking at it locally in some small local region. And then you have another of these. So let's say this one was described by, this was described by some group element G1 inside, sorry. Let me try again. Okay. So we have one operator corresponding to G1, which is, so I keep, okay.
I can also ask you at the end again. I mean, maybe if you prefer.
Yeah, so it's a rather quick thing. So we have some manifold M2, and then there is this group element G1 that's associated to it. I'm using the example of a one-form symmetry. And we have some nearby manifold M2 plus something which is boundary of a manifold M3 with an element G2. And as we saw that we can remove the boundaries of one high-dimensional manifold, we can deform this. So I can bring this closer and try to put them at the same location, at the same M2. So when I do that, I obtain an operator which lives at M2 and is described by the group element G1 times G2. So it's a rather trivial example of an OPE of which we usually consider for local operators. Now these are extended operators, and there are no infinities in the OPE because these are topological. So you cannot have some terms in the OPE that depend on the distance. So usually that's how the infinities arise when you try to bring the operators close together. So there are no divergences, and you can just put the operator on top of the other. And when you do that, it behaves like the operator G1 times G2. So in the U1, yeah.
Can it happen that M2 and M2 prime are not separated by a trivial element in the homology?
Yeah, that can happen, and then you cannot perform this OPE. So this is only for operators that are nearby to each other and are not around topologically same cycles.
Okay, thanks. Thank you.
Yeah. Okay. Any other questions? Okay, so now let me proceed to the most exciting part. So we saw that there are continuous one-form symmetries, and we saw that the spontaneous breaking is connected to the existence of a Coulomb phase. And sometimes it also explains the presence of a photon. Now we want to understand what about the spontaneous breaking of a discrete one-form symmetry. And this is where it will be related to confinement and deconfinement. Right. So for a spontaneous breaking of a discrete one-form symmetry, we are going to study the spontaneous breaking only in a gapped system. So we are going to assume that the infrared is gapped. The examples are pure QCD is believed to be to be gapped in the infrared, and minimally supersymmetric versions of pure QCD are known to be. I have a lot of evidence that they are gapped in the infrared. So we'll be focusing on these examples, and then we will see that when it's gapped, the spontaneous breaking of a discrete one-form symmetry corresponds to deconfinement. And in case it does not spontaneously break, that corresponds to confinement. Okay. So as I said earlier, in case, so if you have a symmetry in the ultraviolet, it's preserved along the RG flow, and the infrared system also needs to have that symmetry. This has been used a lot in, for example, 't Hooft anomaly matching, which constrains the infrared dynamics. Here we are not looking at any 't Hooft anomalies, but just a higher form symmetry, which should also be preserved along the RG flow. And then it constrains whatever the infrared physics is. If it's gapless, it needs to be a physics that admits such a symmetry. And if it's gapped, it needs to be some sort of a gap theory in the infrared that admits a one-form symmetry. We are going to focus on Z2 as an example for discrete one-form symmetry. And as I said earlier, one can actually go ahead and classify what are all the possible gapped phases that can be consistent with a symmetry. So this can be thought of as a mathematics problem of asking what are the infrared 4-dimensional topological quantum field theories, because a gapped system is described by a topological quantum field theory. What are such topological quantum field theories that admit a one-form Z to one-form symmetry? And that can then be classified using the mathematical tools that have been developed in that field. So one can go ahead and one finds that there are essentially these three possibilities in this case. And they take the following form. So two of them are very trivial in the infrared, and one of them is non-trivial topological quantum field theory in the infrared. So let's start with the most trivial setup. So in this, what the infrared theory is just a single gapped vacuum. Any excitation above it is gapped. There are no interesting operators in the infrared. All the operators are identity. All the extended operators are identity, and nothing interesting happens. So that's what I mean by the trivial infrared theory. And then one also needs to impose a Z2 1-form symmetry on it, and that acts trivially on it. So one says that the way one is performing with this symmetry is by using the identity operator. So I need to choose a codimension 2 operator in this theory. I simply choose it to be identity operator, and that's it. So identity operator squares to identity operator. So the Z2 law is obeyed. It's a very trivial way of realizing the symmetry. It doesn't act on any degrees of freedom. So this is one possibility. And this will, as we will see, corresponds to confinement. The second possibility is slightly more interesting, but it's also interesting in a subtle way. So in this case, the infrared is trivial, and the Z2 1-form symmetry is implemented by an identity operator. But something interesting happens when these operators cross each other. Sorry. So something interesting happens when these operators cross each other. So we have some M2 and M2 prime. At their intersection, there are some interesting things that happen. So one says that the Z2 1-form symmetry is non-trivially realized. In a more condensed matter language, such a phase would be called a symmetry protected topological phase, which are phases that are essentially trivial, but the symmetry makes them non-trivial. And these, in standard particle physics terminology, are what are known as oblique confining phases. Then finally, the most non-trivial one is that in the infrared, we do not have a trivial theory. We have a non-trivial topological quantum field theory, which is a gauge theory based on the Z2 gauge group. It's non-trivial because it has non-trivial extended operators. So it admits a topological line operator and a topological surface operator. And then this one is not identity, and this is what generates the Z2 1-form symmetry in the infrared. And this corresponds to deconfining phase of a gauge theory. So this is a quick preview of where we are headed. And to get there, let's focus on some example which has a Z2 1-form symmetry. So these are going to be the SU2 and SO3 gauge theories. So let me quickly discuss these theories. So here we just have let's begin with a pure Yang-Mills theory based on a gauge Lie algebra described by the Lie algebra SU2, where the Lagrangian has a triplet of gauge fields. And this is the gauge algebra index, SU2 index, which takes 3 values. So as long as you just specify the Lagrangian, you're only using the data of a Lie algebra, and you're not specifying what the gauge Lie group that you're choosing is. And it's known that there are 2 such groups which have the same Lie algebra. One of them is SU2, which is simply connected. So it has pi1 is 0. The first homotopy group of is 0. and is the maximal group that you obtain by exponentiating the SU2 algebra. Then there is another group. SU2 has a center which is Z2, which are the elements that commute with the whole group, and you can mod out this central subgroup, and then you obtain this group which is subtly related to SU2, so the SO3 group, and this one has pi1 not equal to 0. Pi1 is Z2. Okay. So there are two theories one can actually choose, which are based on the same Lagrangian, depending on what group that one chooses, SU2 or SO3. And the distinction between these two theories is in the probe particles that one can insert in this system. In the SU2 theory, one can insert any kind of probe particle. So probe particle now carries representation of the gauge group. You can consider inserting any probe particle carrying any representation of SU2 in the SU2 theory. In the SO3 theory, it has to be a representation of SO3, which are the integer spin representations. So in the first case, one can have both half integer and integer spin probe particles, while in the second theory, one can only have integer spin probe particles. So these are the two theories. We need to keep both of them in mind because SU2 theory will only show confining phases. And to see a deconfining phase, we have to go to SO3 theory. Right. So both of these theories have a one-form symmetry, but it's of different type, as they already discussed about it. So there can be two types of one-form symmetries, electric and magnetic. And one of the theories has an electric symmetry and the other one has a magnetic symmetry, which we can quickly understand as follows. So let's consider the SU2 theory first. Before we pick a group SU2 or SO3, we can just study what the gluon, what's the dynamically charged matter content, which are just the gluons. As is well known, they just carry integer spin under the gauge group. So they screen all probe particles which have integer spins. So if you have half integer spin probe particles, they cannot be screened, and there is some a physical charge that can be detected, a physical one-form symmetry charge. So such particles exist only in SU2 theory, and hence SU2 theory has a Z2 one-form symmetry because of this reason. The charges are carried by half integer spin Wilson lines. And it's because of this reason, it's an electric one-form symmetry. Okay. Now in the SO3 theory, there is a different reason why there is a Z2 one-form symmetry, and it's a magnetic one-form symmetry. So now the dynamical objects that we have to consider are not gluons, but magnetically charged dynamical objects. So we know that there are two Polyakov monopoles in such a theory, which are dynamical. And if we look at it from far away, the core of such a monopole looks like a Dirac monopole of an abelian gauge theory, which cannot be constructed dynamically in an abelian gauge theory, but we are in a non-abelian gauge theory. Okay, and it looks like a Dirac monopole for some U1 inside the group SU2. Or if we think topologically, U1 is an S1 and SU2 as a group has the group manifold S3. So inside S3, we pick some S1 inside of it. And the property of all, now we also look at probe particles that are magnetic. And all the magnetic probe particles in the SU2 theory have the same property, that because it is the SU2 theory, they all look like Dirac monopoles for some U1 inside SU2. and hence they can be screened by Thuph-Polyakov, dynamical Thuph-Polyakov monopoles. This is a magnetic screening. But in the SO3 theory, there are new magnetic probe particles because pi1 was non-zero, the first fundamental group. So there are extra circles inside S3 mod Z2. So we are modding out in terms of S1, in terms of S3, we can now have half circles, which are circles inside S3 mod Z2 when you identify these 2 points together. When you identify these 2 points together, it becomes a circle in SO3 group manifold, but it's not a circle in SO2. So these kind of probe particles cannot be screened by Thuph-Polyakov monopoles, and hence one has a Z2 magnetic one-form symmetry. So this is a diagram for the spectrum of line operators of these theories. In SU2, we have a Wilson line in half integer representation, which I will denote as W. This is the electric probe particle. This one is charged under the one-form symmetry. We have integer spin Wilson lines that I will denote by 2 times W because they can be obtained by combining 2 half integer spins. These are uncharged. And then we have probe monopoles which do not quite have the most irreducible charge. They only correspond to circles inside S3 and not in S3 mod Z2, which I will denote by 2H. In the SO3 theory, we have such a magnetic probe particle, which are also known as Thuph lines. And that's the reason for this letter H. And these are charged. This is the circle inside SO3, which is not in SU2. We have these kind of integer spin Wilson lines that are uncharged, and these kind of all the circles inside SU2, the Thuph lines corresponding to them. So this is the spectrum of charged and uncharged operators under the one-form symmetry. Okay. And now one final ingredient that we need to understand to close this analysis is that these operators that we said do not exist. So for example, in the SU2 theory, we said that the most fundamental Thuph line doesn't exist, the one corresponding to circle inside SO3. That's actually not quite true. It does not exist as a gauge invariant operator on its own, but it exists in a hybrid kind of form. So here is the topological operator that generates the Z2 one-form symmetry. It's a surface operator. And it can be recognized as a Dirac string for SO3. So it's a Dirac string for SO3. And if you try to end it, at the end of it, one can realize such a Thuph line or such a magnetic probe particle. In other words, if you try to have in an SU2 theory an SO3 monopole, then it leaves behind a Dirac string which is physical, which is not completely unphysical. And the physical Dirac string is precisely the one-form symmetry generator. And similarly, one can now fuse this with the Wilson line, the half integer Wilson line W, and obtain a dionic line operator that lives at the end of a Dirac string, W plus H. So these line operators seem to be missing from our spectrum, but they are there as in a different form, as what are known as non-genuine line operators. Similarly, in SO3 theory, there are these, the magnetic one-form symmetry is generated by operators of this form in terms of second Stiefel-Whitney class for SO3 bundles, which is a Z2 valued class. And you can write the topological operator in this form. And at the end of it, you can realize a half integer spin Wilson line and the dionic line. Okay. And now let's see how all of this can help us in characterizing phases of minimally supersymmetric pure Yang-Mills theory. So we consider n equals to a Yang-Mills theory, which has n equals to 1 supersymmetry with 4 supercharges. This has the gauge fields for SU2, and it has also an adjoint, a Weil fermion in adjoint representation. So we have not added any half integer spin dynamical particles. Adjoint has a spin 1. So the Z2 one-form symmetry of SU2 theory is preserved, and we have not added any magnetic dynamical particles. So the Z2 one-form symmetry of SO3 theory is also preserved. So even with supersymmetry, you have these Z2 one-form symmetries. And now it's very well known. It's expected to have 2 gapped vacua in the infrared. And as famously it was shown in the paper of Seiberg and Witten, that these 2 vacua can be exhibit monopole and dion condensation. These are limits of such 2 such vacua, but I'm going to suppress the subtlety. So they exhibit monopole and dion, a condensation of dynamical monopoles and dions. Right. So, and that leads to a dual version of Meissner effect in superconductivity, which leads to confinement and deconfinement, as I will now discuss. So let's study the vacuum in which magnetic monopoles condense. And let's study the fate of these line operators. The 't Hooft, the irreducible 't Hooft, Wilson, and the dionic line operators. And recall, we are doing a computation of this form, where we have wrapped the line operator along a large rectangle, and we want to compute what the potential is. So let's consider, because the magnetic monopoles are condensed, let's first discuss the 't Hooft, a probe magnetic particle, the 't Hooft line. And since the magnetic monopoles are condensed, this just behaves like a Higgs phase, a magnetic Higgs phase. And we know that the potential is constant because the probe particles are completely screened. One can just move them without expending any energy. And if that's the case, V of R times T is like, it behaves like the perimeter of this loop. And then it's often said that the 't Hooft line is exhibiting a perimeter law in the Wilson and 't Hooft's characterization of these phases. Now, these 't Hooft particles, probe particles, can be infinitely separated because there is no potential between them, and hence they deconfine. They should arise in the infrared theory. So it becomes some line operator in the infrared theory, and the infrared theory is topological, so the line operator has to be topological. So that's the fate of the 't Hooft line. For the Wilson line, we have a Meissner effect kind of situation going on, because the magnetic monopoles condense, any electrically charged things will confine. And they exhibit the potential between them takes the linear form. And the Wilson lines thus exhibit area law because you have an R times T behavior. In such a situation, you cannot separate them infinitely far away using finite amount of energy. So such particles confine in the theory, and they do not appear in the infrared. The same happens for dionic particles because they are also not aligned with the magnetic particles that have condensed. And so they also show an area law, they confine and do not survive in the infrared. Okay, so that's the fate of these lines. The 't Hooft line survives in the infrared, while the Wilson and the dionic lines do not survive. So what does it mean? Let's consider the SU2 theory. So in the SU2 theory, the 't Hooft line, the only line that survives in the infrared is the 't Hooft line. And as we saw earlier, it's attached to some topological operator in the infrared. This is the only configuration that is there in the infrared. There are no other line operators, the genuine line operators. So it's a trivial theory in the infrared. And since this 't Hooft line is uncharged, the one-form symmetry is completely trivially realized in this theory. So this leads to the confining phase because the charged particles were the Wilson lines. They are confined. It's a form of confinement. And it's described in the infrared by this trivial Z2 one-form symmetric phase. So in the language of Landau kind of language, this corresponds to one-form symmetry being unbroken. This is our first example of a one-form symmetry being unbroken. And let me call it's broken in a type 1 fashion, because there is another way to there is another way to preserve it or leave it unbroken, which will be the oblique confining phase that we will see later. So now we can look at the SO3 theory. In this case, the 't Hooft line was there in the ultraviolet as a genuine operator. So there is a genuine line operator that survives in the infrared, which is non-trivial. So the infrared theory has a non-trivial line operator. And that's precisely the property of a Z2 gauge theory. So the infrared theory is not trivial. It's the Z2 gauge theory. And it corresponds to Z2 one form being broken because the order parameter for it, the 't Hooft line which was charged under it, survives in the infrared, acquires a non-zero wave. Right. So before I move to the dionic vacuum, let me ask if there are any questions about the fate of operators in magnetic vacuum. Okay. So we have seen that in this magnetic vacuum, the SU2 theory confines, and that corresponds to a trivial one-form symmetric phase. It corresponds to Z2 one-form being unbroken. And the SO3 theory, on the other hand, it deconfines. And this means that in the infrared, we obtain a Z2 gauge theory, and it corresponds to one-form symmetry being broken. Let's study the other vacuum, the dionic vacuum. So here what happens is that we have dynamical dions that condense. So these are also referred to as Julia Z dions. And now let's study again what's the fate for the 't Hooft, Wilson, and the dionic lines. The 't Hooft line is not aligned with the dionic charge. So again, they confine, they show an area law, and they confine. The Wilson lines, the same fate happens for the Wilson lines. They're not aligned with the dionic charge. So they are also confining. While the dionic line, it aligns with it. So it shows like a Higgs kind of behavior, and it deconfines. So the only line that survives in the infrared is the dionic line now. And then we can analyze the two theories again. In both of these two theories, SU2 and SO3, the dionic line was attached to a non-trivial surface operator. It was a non-genuine line. So we found that we must have a phase in which the infrared theory is trivial. There are no non-trivial topological operators in the infrared. But this is different from the phase that we encountered earlier. This one, where the operator, the non-genuine line, was actually uncharged under the one-form symmetry. Now this, in both of these theories, this dionic line, because it has both W and H, it is charged under the one-form symmetry. So the one-form symmetry is not realized quite trivially. There exists a subtle phenomenon, a string kind of, and there exists an order parameter which is charged, even though it looks like a hybrid of lines and surfaces. And this is the hallmark of what are known as symmetry-protected topological phases. So what we are discussing is a non-trivial SPT phase for the Z2 one-form symmetry. This also corresponds to one form being unbroken because the charged lines, the Wilson and the 't Hooft lines, do not arise in the infrared. They're confined. But it's a different form of remaining preserved, and we can refer to it as a type 2 spontaneous unbreaking of Z2 one-form symmetry. So let me summarize the main lessons here. So we've seen that confinement is the same, can be phrased as one form symmetry being remaining unbroken in the infrared. And deconfinement can be phrased as one form symmetry breaking spontaneously in the infrared. Now, if we look at the confining case, there can be various possible patterns of confinement. For example, it can be trivially confining or it can be obliquely confining. These are the two kinds of situations we saw. Or there can be more integrate patterns of confinement. But this perspective of one form symmetries tells us that all these patterns of confinement, instead of trying to understand them by brute force, we can rephrase them as that they are SPT phases for a one form symmetry. And then one can extract out this problem. One can ask, what's the mathematical structure of SPT phases for any kind of symmetry? And this problem has been explored a lot in condensed matter and mathematical physics literature over the last 10 years or so. And the main general lesson has been that as a first approximation, SPTs are classified by cohomology groups of classifying spaces. So for the usual symmetries, usual discrete symmetries, they're classified by cohomology of the usual classifying space. And for one form symmetry, higher form symmetries, they are classified by iterated cohomologies of iterated classifying spaces. Now it becomes a sharp mathematical problem. If you want to classify all possible patterns of confinement, you can simply ask what is the classifying space and compute its cohomology group, and that will describe all the possible confinement patterns. In our case of this 4 dimensions, the group is denoted like this, the cohomology group that we want to compute. So this is just to give you a flavor of how a physics problem of understanding patterns of confinement can actually be phrased, becomes a problem in mathematics that can be concretely solved. And now finally, if we have deconfinement, as we saw, it results in a discrete gauge theory in the infrared. And one can similarly ask what are the various kinds of discrete gauge theories. These are known as digraviton gauge theories, and one can also classify and study them. Right. So these were the main lessons. And now let me describe briefly what are generalized global symmetries. So we have seen that usual symmetries, we have rephrased them as topological operators of codimension 1. And they're very special kinds of codimension 1 operators because they're invertible. They're described by the structure of a group. You can compose them, and then there always exists another operator that can annihilate one of these. And the mathematical structure, as we all know, is just the group theory that controls these symmetries. In this talk, we saw how we explored one of the generalizations, which is to generalize the codimension of these topological operators while leaving invertibility intact. So if you perform this generalization, one lands on what are known as higher form symmetries. And the mathematical structure to describe them is a higher version of a group. It's a categorical version of a group, which is known as a higher group. We didn't delve into this, but this is what the full mathematical structure is. There is another generalization that one could have performed. While one could change the codimension or not, keep it preserved, but drop the condition that they are invertible. So as one allows non-invertibility, this leads to what are known as non-invertible symmetries that Arthur will discuss in the final talk in this series. And these non-invertible symmetries, the mathematical structure for them is that of a fusion higher category. So the reasons for this were elucidated in our paper from around 2 years ago. And this is more complicated than that of a higher group. Higher group are special examples of fusion higher categories. So these are the main types of generalized global symmetries. If you get into the realm of fusion higher categories, These are the most general discrete global symmetries that can exist in relativistic quantum field theories. So this is the most general mathematical structure to look for as far as discrete symmetries are concerned. So this was a brief outlook. And now let me conclude. So we have explored higher form symmetries using the examples of one form symmetries and 4D gauge theories. These symmetries are invariants of RG flows, and they can constrain infrared physics, whether it is gapped or gapless. We saw that the possibilities for gapped infrared physics can be classified, like in the example of confinement and deconfinement. And so this can be used in understanding confining, deconfining phases of asymptotically free non-abelian gauge theories, which is a non-perturbative problem. Right, so, and in this is only one of the applications of higher form symmetry that I have discussed. One can apply them in various other contexts, like in 3 dimensions. One can understand Chern-Simons matter theories and their phase diagram using them. People have also applied them to understand 5-dimensional and 6-dimensional superconformal field theories, which are all intrinsically strongly coupled, so they do not admit a Lagrangian description. And people have also looked at 4-dimensional versions of such strongly coupled theories, where you have some minimally supersymmetric CFT. So it's a conformal field theory to begin with, but then you gauge some of its symmetries. So it acts as some generalized matter content. And then this initiates an RG flow, which is rather like the RG flow in asymptotically free non-abelian gauge theories. And one can determine whether these are going to confine or not with inputs from string theory or M theory. And people have found that there are actually confining phases in such non-Lagrangian theories as well. So these symmetries, when combined with other tools, can be extremely useful in characterizing strongly coupled infrared physics or strongly coupled physics in general. So let me conclude my talk here. Thank you very much for your attention.
Thank you very much, Lakshya, for this very interesting talk. And I guess we already asked a lot of questions, but are there any further questions for Lakshya? If you have any questions, please just unmute yourself. Maybe I can start with one. I wonder if the same techniques can be used in curved space-time, like if you replace your non-abelian gauge theory with curvature. And yeah, thanks.
Yeah, so these things are for any kind of space-time. So if you're in curved space-time, you won't be studying phase structure anymore. But you can study other problems, and these topological operators can be defined in still as a submanifold inside whatever space-time that you have. So you can have a 4-dimensional space-time manifold M4, and inside it pick some M3 or M2 and define these topological operators. And you can they would constrain correlation functions, correlation functions of operators in the theory on such a manifold M4.
So just to make sure, so gravity as a dynamical field, like if I replace F mu nu with R mu nu.
Ah, I see. So you want to have dynamical space.
Yeah.
I thought it was a fixed background. Yeah. So if you have gravity, there is a standard law that coming from the Somplan program that gravity should not have any global symmetries, which essentially follows from the fact that in a theory of gravity, there should be no gauge invariant operators. So one often talks about there are no gauge invariant local operators in a theory of gravity. And the same argument extends to extended operators. So in particular, you cannot have topological operators. And so there should be no, as a corollary, there should be no symmetries in a theory of gravity, in a consistent theory of quantum gravity. And this can be used then to classify, as people do in swampland program, to classify what kind of theories can be consistently coupled to gravity and which cannot be consistently coupled to gravity. And the ones which cannot be consistently coupled to gravity will have some symmetries that cannot be removed. And they then go, they're then part of the swampland. So one can have these kind of applications of symmetries in gravitational physics.
I see, but maybe some anomalies like Weil anomaly or like trace anomaly, can the same technique can be used in that case?
Yeah. So these are anomalies. The Weil anomaly is related to space-time transformations. And what I was discussing here, so they're examples of standard symmetries. What I was discussing here is generalization of global symmetries, which are all internal symmetries, not involving any space-time transformation. So there has been very little work that has been done in extending these generalized symmetries to include space-time symmetries. And this is something which should be explored and has a lot of potential to be explored in the future.
I see, but I guess the main issue is that there is no this queen connection between your degrees of freedom when it's the symmetry of the space-time and it is spontaneously broken. It's not like directly related to the number of Golders and bosons that you have in the system. Is that a correct understanding?
Yeah, something like that, because we are describing the symmetries as topological operators that can be inserted in space-time. And space-time symmetries act on space-time. So now the question is what are there topological operators corresponding to symmetries that act on space-time, and in what sense are these operators? And it's also very much important in understanding crystalline phases of matter in condensed matter physics, which have crystalline symmetries that act on the lattice.
Thank you very much. Are there any more questions for Lakshya? If not, then once again, I would like to thank you and all of you that join and asked several insightful questions. And yeah, thank you very much.
Thank you very much for having me.
That was a pleasure, and thanks a lot. I guess now we can finish the meeting, and let me